today, I mean, last time we saw a basic CLI command line interface, and we learned that everything is a file in the end. I mean, it may not be very much absorbed in you right now, but as you move ahead, you will see that everything is really a file. And were you able to try some of the things, or were you able to install Windows subsystem or Linux?
No, actually, I saw the videos, but I was not able to stop it. I mean, not able to work. I didn't have time. So, yeah, currently speaking, I didn't have time. I read the notes. I read whatever we read on the same day itself. But this week was, I mean, I was very busy this week with some submissions. So
Okay,
yeah,
no problem.
only.
Uh, Today I was thinking, how about we pick up one particle, just one,
Yes.
because that is very simple. Like just one thing, we will try simulating that, and then we will try to move towards Argon case.
Mhm.
Okay. So, let me say, something
Uh,
of, uh-huh.
Sorry, I was just interrupted you. I want to tell you that we will be connected. I mean, at least for at least 3 months or 4 months, because I think I will need time to understand and learn.
Of
And
course.
also, I want to learn this. It's called Monte Carlo simulations, which is included in Molgadam. Is it that? Somebody told me you have to learn those things as well.
So, once you know the concept of what it really does and how it samples configurations, that's what is really needed to be learned. Um, yeah, once you grab the concept of molecular dynamic simulations,
Mhm.
you should have enough fundamentals and basics
Mhm.
that you can run Monte Carlo simulations using LAMMPS.
Okay.
So in order to be able to do even Monte Carlo simulations and make, just to be sure that what you're doing is the right science,
Mm.
you do have to learn the basics of Monte Carlo, the theory part.
Okay.
Yeah. And as far as lamps goes, you just have to, give it a few commands.
Mhm.
Yeah. And it will run Monte Carlo for you.
Oh, okay. That's
Yeah.
good.
But it's
Okay.
it's it's really important that we know how it does so that
Mm.
we do it the right way. Yeah.
Mm.
Like
Okay. No
for
problem.
for example, I'll give you um so often we try to simulate we try to mimic macroscopic scopic scale properties, right? Like what would be the density of water molecule in a beaker in real life,
Mm.
right? At this
Mm.
temperature and pressure, and I want to simulate that. I can't simulate overwhelmingly large number of atoms, molecules. Like
Mm.
in that system, there are going to be I don't know how many Avogadro numbers of molecules,
Okay. Yeah.
right? It's huge, and computers can't compute that many things.
Mm.
So we'll try to simulate just 500 water molecules because that is like really a finite number which we can do on computers and to mimic the temperature and pressure of what it is in the real room, we would implement a thermostat uh, algorithm, something that will try to maintain the temperature of this system, 500 watt molecules, right? And temperature is basically kinetic energy, coming from kinetic energy. Right? And there are nice theories that tell that you can calculate temperature using these things just by force, yeah, just by kinetic energy basically of these atoms. Um, and so thermostat is going to basically somehow manipulate kinetic energy of your entire system in a way that the temperature is maintained to a target temperature that you want. And then there is going to be barostat, which you want to implement when you want to maintain a pressure in
Okay.
your system, right? You want to simulate water at 100 atm.
Mm.
And so that for that, you're going to need some barostat algorithm, that manipulates coordinates and
Okay.
box dimensions in a way that uh, it stays it behaves like more like a real system. So now,
And one quick question. Uh,
mhm,
as I have seen, you have been simulating a polystyrene, right?
Uh-huh.
So polystyrene are the large scale molecules. You have many units, millions of units. How do you do that in a computer simulation? Do you only take a little bit of it?
Right. So when it comes to simulating large molecules, polymers, RNA, DNA, you have to take the smallest representative molecule. Okay. So for instance, for me, if I want to study the diffusivity, okay, what is the smallest number of monomers that I can take, run simulation and get by? Okay, something so that I don't necessarily need to simulate millions of monomers connected together. Uh, so yeah, you can run probably a sensitivity analysis sort of, right? You can take 10 monomers, 15, 20, 25, and then calculate diffusivity. As long as it's varying, you're not in the good zone, right? You want to keep
Okay.
increasing that.
Mhm.
Yeah, so that's how you can find like what should be the minimum that I should take. And also always literature and whatever theory based on that you can pick.
Sounds
Yeah.
good. Let's start.
So I was saying, all right, so in lamps we can write implement thermostat and barostat by writing just one line of command
Okay.
and but not knowing not knowing how it works is going to lead to troubles. Like
Yeah.
for example, why did I start telling about barostat and thermostat? Because I wanted to tell you that it's really important that we know theory behind it.
Mm.
So for instance, if you implement thermostat and keep uh, damping parameter of the thermostat to be say 50, okay, or 10, because you noticed that when the damping constant is higher, say above 100, your temperature fluctuates a lot, okay. So
Okay.
what you might want to do, what you can actually do is reduce the damping factor, okay. So what it does is it will um, reduce the thermal fluctuations in your system, okay? And you might like that because there is no thermal fluctuation. The temperature is being maintained perfectly well. It's good, right? But that's not necessarily good because you're not really then simulating the right system. You're not
Mhm.
simulating what you want to simulate. Numbers look good, plot looks good, but it's not what you want. And so knowing what exactly your damping constant or parameter of the thermostat is doing is important. That's why. And so it is started because I wanted to tell you that Monte Carlo simulations we can do in LAMPS, writing a few lines of commands, but knowing the basic is what will take time, to be honest. Yeah. Okay. So today we will see first how we can simulate one particle, what really simulation means or modeling means.
Okay.
Um, I have so you know what is Jupyter notebooks?
Hello.
So Jupyter notebooks and the more modern version is Marimo. I'll
Yes.
show you
Mm.
here. So there is one called Jupyter notebook, okay, and then there is another called Marimo. So programming languages allow us to perform calculations very fast.
Mm.
Um, and they allow us to write complicated equations
Mm.
easily, right?
Mm.
And programming languages allow us to do many things, right? Including the thing that we see here, like this web
Mm.
page, for instance, HTML, JavaScript, or CSS, everything. And Python is one of those. Python is one of those. It's a high-level programming language, which means the syntax that you see, the way it is written, it's very natural. It's easy for us to understand. You'll see that in a minute. And so we will be using Python to see that one particle Brownian motion. Okay, that's what we are going to do. And so, yeah, we'll be using Python code, a little bit of it, not a lot. It's good to know. So there are many ways we can run Python. Okay, you can just write, maybe I should open a new terminal. Yep. We're gonna go to Dr. Lok directory, and this is where we are, right? You can write a simple file. Let's just create. So this is the file that I was actually working with, and I was just writing those simple codes so that I'm ready for this tutorial. Um, Nano, I'm
So,
just gonna call it 1.py. And this is my Python file, okay? I can say, I can write my Python script, Python, whatever I want Python to do, I can write here and then ask Python to, do this. So here, for instance, I can say x equals 2 and y equals 2 and print x plus y. This is like the very simple thing. You can see it, read it, and understand it, what it means and what it's gonna do, right? And let's just exit from here. So that's what I have saved. You can see the contents of that file here. This is what the file contains, right? So don't worry about it. Perfect. Now I'm gonna say Python. That's the interpreter that I have. I'm just gonna say, hey Python, can you please read this file? Hey Python, can you please read this file? And in that file, I ask Python to, assume that x is 2, y is 2, and then I am also asking Python to print the value of x plus y, right?
okay.
So, and then I run it, and Python tells me, hey, you asked me to print x plus y. Here is the answer, 4.
Okay. So I have questions. We are running this code into this terminal app, right?
Yes,
So how you embedded Python in it? Is it like you can embed anything in it? MATLAB, Python, C++.
right.
I think I
So,
learned actually I learned C++, but we had a
mhm.
different different GUI based thing in C++ where we used to write and run the code. Same is with MATLAB. We have different software than MATLAB. So how does the Python work? Doesn't that Python has its own GUI?
So, it if you are on a Windows machine, I'm not sure how that works on a Windows machine. You might need to install Python interpreter. Uh, on Linux-based operating systems, Python is
Okay.
usually packed. It comes with the operating
Okay.
system.
Okay. Okay.
So yes, if you look at here, like for instance, Python, I say Python and it says, oh, Python not found. What about Python 3? Yeah, there you go. I wrote Python 3 and it has started a Python terminal for me.
Okay.
So now whatever command I write, Python will be taking care of that. Like right here, I can write x is 23, y is 2. Oh, sorry, I forgot to add equals, and then you can print whatever, and there is the answer. So this console is like a playground,
Okay.
Python playground, like a Python
Python thing.
playground. Yes.
I got it.
So
So
Python
you called
comes with,
you called Python for running this calculation.
yes. So here you can see this is like a Python playground where you can, do stuff right away. And this is also one way you can write everything in a sequence of instructions. You can write in a Python file and then ask Python to just read it and do whatever is written in that file, right? So that's what Python did here, It read and did what you asked it to do, right? So that's Python basically. Another way of running Python scripts, because this is like here, now if I want to go and change y equal to 2, this 3, I will have to rewrite y equal to whatever I want, like, 4, for instance. I do have to rewrite. I can't go back up there, like with my cursor and change that 2 to 3, okay? So that's like terminal. But I can do that. I can just, go to my file 1.py and then I can just do it, here, change that. save the file, and ask Python to do it again, right?
Okay.
Uh,
So
yeah,
you just wrote Dr. Alok Python 3 1.py. So
yeah.
what does it mean? Like you never wrote Python to sum up, or you never did anything like extra. You just executed that file, right?
Yeah.
Okay.
Yes, so that's what we did. Where I am getting at is this. There are so many ways you can write Python script, Python
Mm.
syntaxes, instructions, and execute them. Ask your machine to do it for you. So like this is one way you talk to your machine. So this was one way, we are talking to the machine and machine is doing what we are asking it to do.
Mm.
This is another way of doing it, writing everything in the file and then asking Python to do it. That's another way, right? There are many other ways, okay? One of them is Jupyter Notebook. Jupyter
Okay.
Notebook is, yeah, it has been really good. Jupyter Notebook is like you can imagine a big notebook file, okay?
Mm-hmm.
Big notebook file which has little cells where you can write your Python code, okay? And then you can execute that Python code right there, and the output will be right below the cell.
Okay.
Okay, and then you can go to your next cell where you can write your Python code and again execute it, right? So it is like a canvas.
Mm.
Okay, it is like an editable canvas where you can do a lot of things. So
Oh.
the same way there is Marimo. Marimo is another notebook,
Mm.
okay, where again you can write Python instructions and run them.
Mm.
So that's what I'm going to do. I'm going to open Marimo 2.py. Okay, I'm just creating, 2.py here. Okay, 2.py does not exist yet. You can see there is
Okay.
no 2.py file, right?
Mhm.
So we are just gonna go ahead and ask Marimo to edit 2.py. Of course, now this command, this this is something that will come to you with time, and of course the tool that you're using. So you will learn all those things later. For now, we know that we wanted to edit a Python file,
Mm.
okay, called 2.py, and we wanted to do it in Marimo notebook. So this is how I'm gonna open it, and I say that, and it tells me that go ahead, open this URL in your browser. So I'm gonna copy that URL, go to my browser. Oh, it's already open. You see that?
Mhm.
Let me just increase the size a little bit, maybe here. So this is the notebook. Okay, it's a really no, long canvas, and it keeps growing as you write more and more. Okay, so this is the cell. This is where we are going to write stuff. Like here, I can write x as 2. Okay, and then y as 387, and then print x plus y, and then execute that. And there is your response right there. So it is a playground in one sense, but it's also a notebook, Python notebook. Um, okay, and then I can continue doing things. I can again print, um, perhaps here is the answer. And then I can print uh, x plus y. There you go. Here's the answer 389. So you see, the fun fact is that the x and y values are still in the workspace. They are still in the
Mm.
memory. So when I ask it to print this, it knows what x means, what y means, and what I'm
Mm.
supposed to do with those two, right? And so this will continue basically. So that's basically Marimo notebook.
Mm.
And yeah, this was just a little bit to give you what we are going to do. Let's do it. Let's do it. Oops. All right. So we are going to do particle, like we will just take one particle, okay, and we'll do Brownian dynamics of that particle. We'll try to simulate that, okay. So I'm going to say import math, import random, import math and import random. Python understands what those two things mean. Import math will um, give you a lot of functions that are already written that you can use. For instance, if you want to take a square root of a number,
Mm.
like for instance here, y is 5 and you want to take it's a square root. How do you do that? We know that in math there is
Mm.
there is like
Yeah,
a
square root
set of
set. Oh.
instructions that you have to do,
Mm.
right?
Mm.
But here here
Mm.
we can import that function which will calculate a square root for us. Okay, so we
Okay.
can just say then sqr, oh sorry, math.
So, is it a math library? Can
Yes, it's a math library. All right, there you go. So, so you see, this function is made available to you so that you can calculate the square root of 5 by this library.
oh,
The same way, random library will allow us to create some random numbers that follow certain patterns.
mm.
So, in order to simulate that one particle's Brownian dynamics, we're going to have define that particle, right? We are going to have to choose a time step, um, some random number generator seed value, maybe if we need that,
Mm.
right? And how many steps do we want that particle, do we want to simulate that particle? That also we need to define, right? All right, so I'm just gonna initialize some of the variables, like number of steps. Say we want to simulate only 1,000 of it, okay? The time step, say we are taking whatever time step that we are taking, and then diffusion, that means how much we want to move that particle in a time step, in a given time step. I mean, we don't have to use all of these things, but when we use these things, we make sure that we are actually doing the Brownian dynamics. Um, and why do we really need this DT and this diffusion and this number of steps? You probably know from diffusivity calculation that Einstein's expression for mean square displacement has this d multiplied by t expression,
Yes.
right? Yeah. So that's what we're going to use actually. Um, so we need that dt as well as the diffusion. We can also call it d, of course. Say 1.0, just give that number, okay? And we can just define that. Okay, so we have these simple things already now set up. Um, we we would like to define the particle to be at some XYZ value. It has to start somewhere at some XYZ values, right? So let's just say that the particle is at 0.0 maybe, and 0.0, and Z is also 0.0. That's where my particle is, okay? And we want to change its positions by some amount, right? Say dx amount, okay? If we want to simulate the particle moving, we have to change its position, x, y, z, all those coordinates, right? And so let's just say dx, dy in dz. These are the variables that we are going to need. right? So how much do we really want to change that x value? I can simply write 1, 2, 3, and then it will just change that by that amount. You're right.
So
I can just
will you
add or
be using
subtract. But
random,
that's
right?
not, yeah, but that's not what we want actually. We would like it to follow some distribution, okay? And that is why we have this import called random property library. We'll just say random dot Gauss, and so this is going to give us a random number taken from Gaussian distribution of numbers, okay? And we're going to have to tell it we want a random number between these two numbers, okay? We don't want it to be randomly like, you know, some huge number. We want it to be between these two numbers, 0 and 1, for instance. We don't
Okay.
want the particles dx to change so much that it just,
Okay.
moves out of space, moves somewhere else. Yeah.
Okay.
So we're going to tell it, hey, can you please give me a random number which is between 0 and some step size. Okay. The step size is the maximum that I will allow my particle to move, right? And I have to define that step size because my Python, this notebook still doesn't have that.
Okay.
I'm just gonna say step size is, we can say 2D and probability. D is your diffusion and time is your dt, right? That's your step size. Um, no, wait, we have to take a square root of that.
Okay.
Math dot square root of 2dt. So that's my step size. So now what this will do, it will give me a number between 0 and that step size, okay, which is coming from that calculation. Um, and and that number has to follow Gaussian distribution of numbers. Similarly, we can write the same expression actually. So I can simply copy paste this part and do again here and again here and be done with it,
Okay.
right? Um, there is a problem with this. I mean, I can just run it, okay, but I need to update these values, right? I
Yes.
need to update the coordinates of my particle. It's currently sitting at 0, 0, 0. I need to update that. So how I can do that is by simply writing x equal to x plus dx, right? I can add or subtract whatever I want to do. I can do that. And then similarly, y can be updated with y plus dy, and z can be updated with z plus dz, right? This is how we can do that. Now, if I run this right now, um, it will move by one step, right? The particle is at 0, 0, 0. We get some random numbers, okay, x, y, z, and
Okay.
we add that and then update the position. That happens only once.
Once.
We want it to happen 100 times, right? And for that, we have to run this calculation again and again 100 times, right? So we have to loop. We have to do it again and again 100 times. Okay. So how do we do that? I'm just gonna cut this guy and write it in a loop for, this is just one of those things you can do in Python. For I in range, I'm gonna say number of steps, and now fix that variable name also. That should be number of steps, and paste that whole command. So here it is. Now what it will do for me is this is the loop, okay? What it does is, look at this, range is a function,
Okay. Nice.
and range की maximum value is hundreds.
Okay.
Well, I think it will go up to 99 probably, I'm not sure. but it will run up to 100, okay, starting from the first number and whatever that is, either 0 or 1, okay? So it will run that many times. So the value of I when it runs first will be 1, okay? When it runs second, it will be 2. When it runs third, it will be 3. So it will run until this number is there, or until this number is met, for instance, okay? I have forgotten all these things now actually in Python. So nonetheless,
Don't we need to provide the value of I? Okay.
right.
Like if I
So
want the value for I to start with 100, for example.
yes. So Python is actually taking from this. Look at this. This will be expanded. Like instead of writing that range, what I can do is I can write this for 1, 2, 3, 4. That's what I'm doing actually. Okay,
Okay, okay.
up to 100. So that's what I have written basically. So I will become 1 and then it will run, will become 2 and then it will run. That's what is happening.
Okay.
All right. So this will run 100 times and it will give us, it will update the positions. Um, okay, let's run it. There is some problem. It says name n underscore steps is not defined. Oh, okay. I did not run that. Perfect. It ran. So we know okay, it has run, but we don't see the answer, right? We don't really see the particle moving. Um, so if we want to see the particle moving, we have to save those x, y, z values somewhere, right? And then look at it moving by plotting it. So that is what we are going to do. This is all, okay? This is the dynamics, Brownian dynamic simulation. This is done. Now we need to look at it so that, we can see what, whatever we are doing is really happening. So here is what I'm going to do. I'm going to print these values of x, y, z, um, x, y, and z. And there you go, that's it. So every time the loop runs, it just gives you x, y, and z values, right? So let's go ahead and copy this and then go back to our terminal. And I'm gonna create a new file, call it Brownian.txt, paste all of that here, okay? Let's go at the top and I'm gonna write, well, we can save it, okay? And then, you know what is OVITO? OVITO, VMD? Those are softwares that will allow you to look at your structure, okay, and do a lot
Okay.
of other things also. I'll show you the example. So let's go to OVITO. So look at this. Do you see this is like they're simulating some sort of massive structure. And see this visualization, where do we do that? So for that, we are going to use OVITO software. See, these guys can see the atoms moving, molecules moving. They have really nice visualizations. I like that. Water molecules moving. They're simulating probably the water dynamics when there are two hindrances, right? All right. So I already have OVITO on my system. Um, But my OVITO needs to understand these XYZ values, these that I have produced, right? It needs to be able to read that and represent it, in some way. Like I would like to see a particle like a ball, placed at origin and it moves according to these coordinates. That's what I want to see. So, um, in order for my OVITO to understand, um, I need to have that particular file format which OVITO can read. So one of those file formats is XYZ file format.
Okay.
XYZ, यानी कि this file has only X, Y, and Z values basically of a particle. Okay, not a lot of information actually. This is very simple file. Look at this. Here is an example. It says you have to add the number of atoms at the top, okay? And then you have to add some comment. That is the second line. And then you can add atoms and their information after that. So this is the file format, and we have to follow that file format so that we can open our file in OVITO. Okay. So what I'm going to do is now, well, so far what we have is this column, and this column, right? We don't have this label, ki this is my oxygen, this is my hydrogen, this is another hydrogen. We also don't have comment. We also don't have how many atoms, are there in our file. You can see that. Head of, let's look at the
We have
file.
time dependent positions, right?
Yes, that's all we have. See, this is what it looks like, our file. We need to have those, little things. So for that, I'm gonna go back to my Marimo and let's do this print. Um, I'm gonna write, well, I don't have to write here. So here I can write my, well, let's just give it some name, imaginary. I'm just gonna call it imaginary particle, okay? So that is the name of my particle. Like here you can see you have this oxygen, right? It says O. What I'm going to write is imaginary. Okay. Run this. So you can see now everywhere each line has what? Imaginary. That means this particle is imaginary particle. I can name it whatever I want, not a problem. You can just give it one single letter. Like you can also call it O. It's not really oxygen, but you can call it O, no problem. Okay. Right. So I'm just calling it imaginary. And then let me now copy this guy, this file. And I'm just going to remove that file first and then recreate it, paste everything here. And at the top, I'm going to write these two things, right? The name of the molecule that I want to give and the number of atoms that I have in that system. So at the top, I'm going to write 1 because that's the number of atoms that I have. And then in the second line, I'm going to give some comments. So I can write this is my imaginary particle and save it. And then we'll try opening it in OVITO.
Not directly.
So you don't have to worry about it right now, actually. But this will basically give me access to OVITO. And
Is
now
it
my
free?
OVITO, say
Does
that?
the OVITO has open access? Like, is it free
Yes,
for
yes,
everyone?
it has both. It has basic version and pro version. Yeah, it has both basic and pro version. Okay, so it says invalid number of particles in line number 4 of XYZ particle imaginary.
All three
That's fine.
negative, right?
Yeah, the problem is that it does not understand our file format. We'll fix that, no problem. Um, Let me see. Let's just call it I in that case and try running again. Okay, we have now I everywhere. And then save that. There's one particle, and I'll just call it imaginary particle. And then try opening again. So the column 1 is particle type. Not really. Yeah, sure. All right, something is definitely wrong. All right, was doing this. Let me look at the file type. Oh, it has to be written again and again. That means print and then just like one. So here is what's going on. I'm gonna try and then probably help you understand. I'm writing there is one particle. This is the label for that particle, and these are XYZ values. This is frame one, okay, and this is frame two, and this is frame three. That's what it is. So each frame needs to have, you know, key how many atoms it has and what is the particle type. Like, is it oxygen? It is hydrogen. So it needs to know this one, like how many particles do you have in that particular frame? Let's try opening this one. Oh, let's just save that and try opening it. No, what's wrong?
There's some spelling mistake.
Oh,
Brownian.
where?
Yeah, nano brownian. Okay. Did you? Okay, you only made. You made a nano brownian.
Yeah, spelling mistake should be fine. So I think there is one more thing that we need to have actually. The second line has to be a comment. So this is like just let's just write comment. Okay. I'm just trying to generate the right file format. XYZ values are anyway same, right? I'm just gonna call it b.txt. Save and then try again opening it. Ah, perfect. It works now. So that's our particle. Uh, can we change a few
Time
things?
time zero.
Yes. I mean, it's actually the frame number 0. Uh, you can compute the time from the expression that we have here. This is the dt, and we have 100, so that should be like what, 150, right? 50. That's it. 0.50 basically. That is the maximum time that we have simulated. Here we go. And let's just play that guy. Do you see that movie? That is like very simple and the simplest, probably the simplest to what we can model, I guess. Just an atom and randomly moving here and there. That's modeling. That's not molecular dynamics, of course. There are so many things that have to come before that happens. But that's it. That's the Brownian motion that we are simulating. Okay, if you want to see more of it, maybe like we want to track uh its lines, trajectory lines. Of so you can see that. Do you see that line?
Yeah, great line.
Yeah. So that's basically where it is moving actually the particle. Just that. It's getting very slow. Leave it. All right. If we wanna go, we can
And
go
we
here.
have two particles.
Oh yeah,
Then
why
it
not?
then it will have been better for comparison.
So if we have two particles, we have to make sure that
Both
those two
the
particles do not
are the
have
same.
overlapping coordinates.
Can have the different diffusion.
Yeah. So would you want to really model in two atoms? Like we can have two atoms, okay? If they are randomly moving in space, then it's no different than single atom because everything is the same, right? It's just that we have to make sure that the XYZ values of the two atoms two particles do not collide, they do not overlap, they can't be in the same XYZ values, right? They cannot be in the same place.
Okay, just I wanted to confirm. For example, if you have five particles, so do we
Uh-huh.
have to again generate these comments, coordinates, and again go to this terminal app, uh, copy that, run that. So it will be a time-consuming thing, right? If we have five different coordinates every time. I
Um,
mean, five particles.
so the thing that we're looking at here is like just 18 lines of code, and this is just to show you that this is what modeling looks like. This is the
Okay.
simulation, okay? It's not really lamps.
Okay, okay. It's
You,
not a
you don't
diff.
have to do
Okay.
all of these things. I'm just showing you so you can, see
Oh,
how the modeling is going on.
we are not yet in the lamps, right?
No, this is not labs. This is just to show you one particle modeling.
Okay.
Yeah. Yeah, we'll go to the lamps now
Mhm.
and we'll simulate Argon
Mhm.
and yeah, lamps will automatically write
Okay.
nicely formatted files which you can open in OVITO. You don't have to
Okay.
worry about that. Yeah. So let's simulate Argon. Um,
Okay, one
we'll
more quick
start.
question. The
Mhm.
Marimo version which you were running now, was
Uh-huh.
it a online web app or is it a file app? Like how are you running that? How you,
I'll give me 1 sec. Yeah. Yes. Marimo was the one that I was running was not online version. It
Hmm.
was running on my computer, but the
Okay.
way Marimo runs is it creates a local
Okay.
server. So you can open that in your web browser.
Okay.
Yeah. It probably has its own, I don't know, some app where you can
Hmm.
actually do all those
Hmm.
things. So you don't have to worry about terminal and then opening in the web, all those things.
Okay. Hmm.
All right, let's do Argon simulation.
Hmm.
Share screen. So when I'm doing things, I often use internet to get help a lot. Okay. Um, so for instance, now we are going to simulate Argon, and I can struggle right here in front of you and show you how to do it, or
Hmm.
I can just go and start with a minimal Argon simulation script and help you understand what's going on. Okay, so we're gonna do that.
Yes.
Um, Argon lamps minimal script. Okay, we are gonna copy this thing. Can you see my
Yeah,
screen?
yeah, I can see.
Perfect. I'm gonna open terminal, connect to the same system, Ubuntu, and then we're gonna go ahead to your directory scratch, Dr. Alok, and let's just create a directory called Argon. and then we will change directory to Argon. And there is nothing in it. You can see there is nothing in it, right? Because we did not create anything. So I'm gonna create the first file. Let's call it ar.lmp. Okay, because it's a LAMMPS input file. We're gonna just call it LMP. You don't have to call it LMP. It can be any extension you want. You can even call it alok.alok. Doesn't matter. Doesn't matter. Okay? You don't even have to call it alok.alok. You can just call it alok, whatever you want to call it. It's just a file in the end. What matters is the content inside it. So for the sake of understanding, so that we remember it's an Argon LAMMPS file, we'll just keep it that way. And let's paste all of that here. So this is what Gemini gave us in the first shot, right? Let's see what this is really doing. Units, LJ. So I'll help you understand each of these and then we will run the simulation, okay? Makes sense?
Sure.
Um, so first we are defining some basic things like what unit are we going to use? Like, are we going to use SI unit? Are we going to use CGS unit? What unit? Okay. LAMMPS has its own units system. I think there are 7 of them. And one of them is LJ units, which is reduced units. We will see what that means. And there is so much more documentation already, and you can go and read about it to understand it thoroughly. And then we have, well, let's just go and look at what units LJ means and what other options exist for us to choose from. Now, one really good resource is lamps.org, this website. Here, this is where you can go to download LAMMPS. Okay, this one has Windows executables as well as Linux. I think this is one. Install pre-built Windows packages. You can check that later. And then there is something called manual under documentation column. We're gonna go there. And this is the manual. It's like a LAMMPS book where you can ask any question about LAMMPS. So we're going to say units and then see what comes up. Here's the first page on units. Okay. So on the left side, you have all these commands and like a navigation bar. On the right side, you have everything that they want you to know about units probably. Okay. So like it starts with units command. The syntax is this. Okay. This is how you're supposed to write. The units is solid. You have to write units. You can't skip that S in the end. It's solid. Okay. Then style is something that can change. Look at here. They tell you that units, sorry, the value of style can be LJ, or it can be real, or it can be metal, or it can be SI, or it can be CGS, and so on, right? So any of these values, okay, LJ, real, metal, SI, CGS, can be in place of this thing, okay? In our case, what we have is units set to LJ, and that is perfectly valid command for LAMPS, right? And you can see other examples are units metal, units LJ. This is how you can use basically, okay? So at the top, there is syntax, how to use it, and style, what are the possible values. And then there are examples, how to exactly write it. And then there is description of all about units, okay? All the description. Here, it starts with this. For style LJ, so what does LJ really mean in lamps? That is what they're trying to tell you here in this portion. Okay. So you can see that when you say units LJ, that would mean mass is defined as this, distance is defined as this. This is reduced units. And this is basically the description. A slightly easier version would be this one for style real. Okay. So if you were to write here, if I go and write real, what will that mean to lamps? That is what they are going to tell you here. When you say real, that means your mass unit is grams per mole. It's not in kilograms per mole. It's in grams per mole. It's fixed now, okay? All the distance values are going to be in angstrom and not in meters and not in nanometer, anything, nothing. It's just going to be in angstrom. So wherever LAMMPS expects distance, it will assume that you're giving it the value in angstrom.
Okay.
So when you define the bond length between hydrogen and hydrogen 0.74,
Mm.
and you define the style to be real, that means 0.74 angstrom. Okay. Yes. Let us look at this one here. If you define the units to be SI and you tell that there is the bond length between hydrogen and hydrogen is 0.74, LAMMPS will take it as 0.74 meters.
Oh,
So that is what unit means to in LAMMPS, okay? So when you define real, that means everything else, all these things have this unit, these units, okay? That's what it is. All right, let's go back to LJ because that's the unit we are using here for argon case. Now we know what is units. The second command is atom style, atomic. So atom style, atomic is the simplest. Um, Atom style will basically tell LAMMPS that I want to store certain information about each atom. And when you say atomic, that means you want minimal information like X,
okay.
Y, Z, and what is your atom and what is probably mass. That's it. There is no charge on it. There is no dipole moment. There is no other thing. Okay, it's just like simplest one. So by saying atom style atomic, let us see what exactly that means to LAMMPS. Atom style. Here again, this is your command. The syntax is this one is solid. Has to be this way. A style, the value of a style can be any of these values, right? So it can be even electron, okay, and it can be atomic as well. And this is what we have there. So once you have mentioned your style, atomic, you can mention arguments. Arguments are not necessarily like really needed. You can do without them. It's okay. Like here, we don't really have any argument after atomic, right? So argument is the third element that we have in that line. And here are the values of arguments. Okay. So for atomic, there are no arguments. For a sphere, if you use a sphere like here, if you set your atom style to be a sphere, the possible values are here. These are your possible values basically. For static slash dynamic particle radii, BPM sphere argument should be 0 or 1. This is again optional, and this is also optional. You don't really have to do it, but you can do it if you want. And then there is another one here. I'm not sure what that means really, TDPD. If your style is TDPD, then in the argument, you can write and species, which is basically how many chemical species you have. Anyways, and then here are some of the examples, how to use those commands, this command, I'm sorry. Atom style atomic, that's what we're using. And then of course there is like a long description, right? So to learn about any of these commands, you can always go and read the description of that command in the LAMMPS manual. But for now, understand that this will allow us to define our atoms and hold XYZ values for those atoms in the memory. Okay. Then how many dimensions do you want? We want to simulate a three-dimensional system. So
Okay.
we just say three. Then, what about boundary? Like, how do you want boundaries to behave? Because it's a finite system, right? It's not like our universe, it doesn't have boundary. Maybe our universe even has boundary. Well, for our system, it has to have some boundary, right? 1 nanometer, 1 nanometer, 1 nanometer. You hit a boundary, you have a wall.
Okay.
So how do you want that wall to behave? That's what you're supposed to tell here. Do you want that? So let us see what are other values. Okay, here it says PPP, which means periodic, which means if an atom crosses that boundary, it should reappear from the other side of the boundary. Okay, that's what periodic means. We can also have fixed, okay, say F, which will probably mean it's just fixed and it's like behaving like a solid wall, I think. Okay, if atom goes there, it will just hit the wall and bounce back. Let's go here and see what we have boundary. So boundary, and then how should be what should be the boundary in X dimension, Y dimension, and Z dimension? And the values, possible values are these. Okay, it can be P, which means periodic. It can be S, which means this one. S is non-periodic and shrink wrapped, which I'm not sure what that means exactly. I have to read the description to understand what that means exactly. Okay, so yeah, for now we are using periodic, which means atoms can move out of the box, out of the boundary from any direction and reappear from the other side of the boundary wall. Okay.
Okay.
Yes. So that actually allows us to simulate bulk systems because if you look at a like a bucket of water, and in the center you create a really small simulation cell, you will see that the water molecules continuously move out and come into the system, right? And that is what we are trying to simulate here with periodic boundary conditions. All right. And then we have create atoms, which is basically about, now we have set up like how we want our wall to behave and what should be the units. Uh, we want to store XYZ values of atoms. We want to simulate three-dimensional system. Now we need to tell it कि हमारे बॉक्स का साइज क्या है. X एक्सल में 1 नैनोमीटर है, Y में 2 नैनोमीटर्स है. And we also need to tell it कि सिमुलेशन सेल के अंदर atoms कहाँ पर रखे हुए हैं, like where are they exactly, and what kind of atoms are they. We need to tell that. So you can see here, this one says mass of your atom type 1 is 1. Okay, so that's in Leonard Jones unit. Okay, unit says LJ, right? So 1 means something. Okay, it's in reduced unit exactly. So and also let's go and check what exactly mass command, how to exactly use mass command. Here, mass, and then I, which is, and this I is atom type. Okay, this is atom type. So let me tell you what is atom type. When in a system you can have more than one atom, and of different type. Like you can have carbon, you can have nitrogen, you can have boron, and so many other atoms. So each atom has its own type. Okay, a carbon can be of type 1. You can call it type 1. Okay, and just to distinguish these different atoms. Okay, yeah. So chemically they behave differently, and that is why we label them differently. We call them a different type of atom. An example, a carbon atom which is sp3 hybridized and a carbon atom which is sp2 hybridized can behave differently, right? They're different, chemically different. Okay, so one of them you can call it type 1 carbon, and the second one you can call it type 2 carbon. Okay, that's a little complicated. We don't have to go that far, but understand that is what atom type means, okay? And then the third is value of the mass. So yeah, you can see that here. We have only one atom type, which is argon. All of them are same really, chemically. They're exactly the same. You can't really tell the difference between any two. So atom type 1 and the mass in reduced unit is 1. And this command is trying to create, oh, let me go from up to down actually. So first we are creating a lattice, FCC lattice with this parameter. Let's look
Okay.
at that, what that means, lattice. Here, lattice, the style of lattice. Style can be simple cubic, BCC, FCC, FCP, and any other, right? And then there is scale, which is basically a scale factor between lattice and the simulation box. Scale has to be equal to reduced density rho for LJ. It's reduced density rho for LJ. All right. Lattice con and for other unit types like SI units or real units, that scale value has to be lattice constant, right? Like the A of your lattice. Nonetheless, for our case, since we're using LJ real, LJ units, this is rho, which I'm not sure exactly what that means. It's
Density.
yeah, yeah, it's some number.
Yeah.
Okay. And then we have region. So that's basically um that will create the simulation box. Okay. Um, 4 in X dimension, 4 in Y dimension, 4 in Z dimension. That's what it's doing basically. If you want to go ahead, let's go and check region box block. In the description, let's see what it is. This command defines a geometric region of a space. So that's your computational domain, basically, like entire domain in which the computation will occur, atoms will live, right? For example, the region can be filled with atoms using create atoms command. Okay. So box is basically name of the region, I think. Let's look at that command. Here, region, that's actual command, and then has to be ID of that command, whatever ID you want to give it, right? So here the ID is box, like it is real box, right? That's the ID. You can call it whatever you want. Instead of box, you can give it some other name like simulation box or simulation cell. You can call it whatever you want. Okay. And then style of that region. In style, you can write delete, block, cone, cylinder. Yeah, you can create a cylindrical box, a cylindrical region of a space, basically, right? But
Okay.
what we are doing is we have block. So style value is block. And what should be the argument if we write block? You can see that from here, examples. Under block, let's go ahead and check how to really use that command, okay? In block, you can write x low, which is the lowest x,
Mm,
highest x,
mm,
lowest y, highest y, and then similarly for z. So those are the numbers that you have to write
mm,
after you have written block,
mm,
right? So you write block and then you write x low, x low, x high, y low, y high, and then z low, z high. That's what you have to write here in this place, basically after that. And that is what we have here. 0 to 4, this is about x. 0 to 4, this is about y. 0 to 4, this is about z now.
mm.
All right. So create box. I think this is going to create um the box that you just defined above.
Mm, mm.
And I'm not sure what that exactly means. Let me check here. Create box. Oh, sorry, create. Oh yeah, that's the command, create box. Let's read the description. This command creates a simulation box. It also partitions the box into a regular 3D grid of smaller sub-boxes. That's totally fine. So the point is, what we're trying to do here is, um, you can see that we have defined the region, right? It's the same variable box, right? Oh, can you see the screen?
Yeah, I can see. Yes.
So region we have already defined, which
Box.
is like 0 to 4, 0 to 4, 0 to 4.
Mm,
And we're calling it box.
mm,
And then we're saying create the box, and we are telling it what that means.
mm.
Like what box do I want to create? Here is the definition of box. Go ahead and read it from here. That's what I'm telling basically. Okay. And this n is basically number of atom types to use in this simulation. In our case, we have only one type of atom, which is argon. And
Mm.
so we write 1.
Okay. Mm.
Yes. So create box, which will have only one type of atom, and the definition of box is given above here.
Mm. Okay.
And then there is create atoms. So
Mm.
we are creating atom of type 1 within the box.
Okay. Mm.
Okay. And that region is already defined. We know that.
Mm. Mm.
So it is going to basically, I think it's just going to use this FCC
Mm.
and the region,
Mm.
and within that region using FCC, it will just fill entire simulation box
Mm.
basically
Mm.
with this atom type, and the
Okay.
mass of atoms is going to be 1 in reduced unit.
Mm. Mm.
Okay, so that's the definition of our box and atoms. Now you can imagine a simulation box filled with atoms. Now
Mm.
we want to simulate it. We want it to start moving, right? And earlier in the Brownian dynamics, what we did is we randomly took numbers from Gaussian distribution and we changed XYZ values.
Yes. Mm.
We want to simulate here molecular dynamic simulations. So we would like to actually model the forces between atoms
Mm.
correctly. Okay.
Okay.
So we would have to use the right mathematical equations to do that. And so this is where we are modeling the interactions between any two given argon atoms. Okay, this is
Okay.
where we are defining that. So let's look at that. The first one is pair style. Pair is any two atoms basically. You pick any two atoms, and what is the pair style? How are they interacting?
I have a question.
Uh-huh.
Uh, I have a question. Actually, we are creating only one atom, right? Is it not
No,
right?
no, no. No, so look at this. We defined the lattice to be FCC with density this much, right?
Mhm. Mhm.
And then we asked our lamps to create atoms in that box. So it's just
Mhm.
going to fill the whole thing.
Okay. Okay.
Yeah, with that density, I think.
Okay.
So it's
Okay.
not just one atom actually.
One.
It's
Okay.
the system is already filled. Yeah.
Field. Okay.
Yeah.
Yeah, I got it.
You know what? It's very much better if I just keep showing it to you also. Let me see if we have that. Um, I don't have that here. What I can do is, oh yeah. Let me just save this thing and run it here. Argon.lamps. Oh, I'm sorry. This is not how we done actually. So lamps is the binary that we will see later how we can install lamps. Okay, we can
Oh,
do
okay.
we can do a baiting on that. My computer has these binaries of lamps. Okay, like
Okay.
we have Python,
Mm-hmm.
remember? The
Mm-hmm.
same way we have here LMP lamps. So this is the
Okay.
command. The moment I
Mm-hmm.
type LMP and hit enter, it starts listening. You can see here, right? The moment I typed it, it just said, "Hey, I'm lamps. This is my release version. This is my name, basically. I'm listening. Tell me."
Mm-hmm.
So I'm gonna just say lamps. My input file, मेरे input file का नाम है argon.lmp. So when I say this, hyphen I, basically I'm telling lamps कि ये वाला जो फाइल है ना वो मेरा input फाइल है, ये मेरा आउटपुट फाइल नहीं है ना? ये मेरा input फाइल है. That's what I'm telling lamps कि this is my input file. Please go and read it, and whatever I say in that file, do that. Okay, and if I hit enter, it will just start doing things, and it did it. It was pretty fast, right?
So he did all the calculations.
It's all done. Yeah,
Oh,
you
so
can
you
see
all
from here.
okay. So where okay. So you saved Argon script in the Argon.lmp, and then you asked
Uh-huh.
you first saved those script in the Argon.lmp,
Right,
ar.lmp, right?
right.
And then you asked LAMP to run that file.
Yeah.
Okay.
I'm just gonna show you like in its steps probably. Let's just call it argon1.lmp and then edit that file, argon1.lmp.
And then analysis, we connect this with OVITO. It will be hard to visualize it. Right?
Yeah, that's what I'm trying to help you understand actually. We'll do that. Let's go ahead and write, not here. Maybe I can do that. Let me just remove all these things so that it's easier a little bit to understand. So write data is one of those commands that allows you to save, your entire simulation data. Write data, and I'm gonna call it argon1.data and control save that file and then run with lamps. Okay, so lmp, then I argon1.lmp, and it's done, right? So it must have done everything that I asked it to do in this particular script. Let's see what that script really wanted lamps to do. And this is what it wanted to do. Initialize units to be LJ, atomic style is atom style, dimensions, 3 dimensions, boundary, all of them are periodic. Consider a lattice FCC with this density. Consider this space domain and create the box, simulation box, with that size. And then create atoms in that box using that lattice density and initialize mass to be 1. That's what I told it, right? And then I said, ki now place all of that information in this file. Okay, let's look at that file, what that file looks like. Data file, that's what we wrote. And here is what LAMPS has written for us. It says LAMPS data file via write data command. This is the command that we used actually. And it says the LAMPS version that you have used and the time step and the units that was set in the script. It tells that, hey, there are 256 atoms and there is only one type of atom. And the dimension of your x, y, z are these. X starts at 0 and this is the maximum of x. है ना? X low, X high basically. And the mass of your atom type 1 is 1. And here is the atomic information, okay? This this hash atomic tells OVITO ki this data file is in atomic file format, okay? This hash atomic. It's important. OVITO reads it actually. So this is just a sequential number 1, 2, 3, 4, 5, everything. And this one
So
is the
256.
yes, that many atoms. And then we have second column, which is atom type. कि ये आर्गन है, ये भी आर्गन है, ये भी आर्गन है, ये भी आर्गन है, ये भी आर्गन है, ये सारे आर्गन है।
हम्म,
सारे का टाइप टाइप है एटम वन। और इसका जो मास है ना वो एक है, इसका भी मास एक है, इसका भी मास एक है, इसका भी मास, सबका एक ही है ना। क्योंकि एक ही है, एक ही टाइप का एटम है हमारे पास और उसका मास
yes,
एक ही है। द फर्स्ट एटम was placed at the origin, you can see that.
yes.
The second atom is placed in this location here. The first column is X, Y, and then Z. These three columns that I've highlighted here are X, Y, Z values in that order.
Mhm.
And then these three X, Y, Z values are how many times that atom has crossed X or Y or Z. So here you can see X, the atom has crossed X boundary 0 times. That's what it means.
Okay.
Yeah. And
Okay,
this
so
means,
this.
yeah, you know what? OVITO uses this information so that it knows कि एटम कितना मूव कर गया है एंड कौन सा एटम बाउंड्री से बाहर मूव किया था और उसको हमने फिर से वापस रखा है, so that we can track
अच्छा,
that information. And that is why these three columns in the end are written. So you can see this is like simplest file format है ना। सभी फाइल फॉर्मेट में ना सबसे पहला कमांड कमेंट होगा। उसके बाद आप लिख सकते हैं कितने एटम्स हैं आपके पास, कितने एटम टाइप्स हैं, सिमुलेशन बॉक्स का डायमेंशन क्या है, masses, and then basically these are headers. Okay, masses, उसके बाद मास लिखना है आपको एक लाइन छोड़ के।
अच्छा।
आप अपने से लिख सकते हैं या लैम्प्स लिखेगा, जैसा भी है ना, दोनों तरीके ठीक है ना। अगर मैं यहाँ पे दो कर दूं और फिर लैम्प्स को बोलूं कि रीड करो इसको, तो लैम्प्स विल इनिशियलाइज मास टू बी 2 इंस्टेड ऑफ 1।
हम्म,
तो यहाँ पे मैं चीजें चेंज कर सकता हूँ, लैम्प्स विल चेंज दैट, आई कैन चेंज एक्स वाई जेड वैल्यू राइट फ्रॉम हियर एक्चुअली। ओके, मैं इसको चेंज कर दूंगा, उधर चेंज हो जाएगा। अ, तो एटम्स के बाद वेलोसिटीज लिखा है इसने, है ना, कि जो पहला एटम है बिल्कुल मूव नहीं कर रहा है, दूसरा एटम भी मूव नहीं कर रहा है, आई थिंक कोई एटम मूव नहीं, हमने अभी मूव किया ही नहीं है एटम्स का एक्चुअली, तो
हाँ,
सारे
हमने
का
डिलीट
वेलोसिटी
कर
0 ही
दिया।
है। हाँ, हमने कुछ किया ही नहीं है, देखो ना आप, सिर्फ हमने सिमुलेशन सेटअप किया है अभी तक तो, है ना। तो नाउ आई वांट टू सी कि कैसा दिखता है मेरा ये फाइल। ओके, तो लेट मी शो यू हाउ दैट फाइल लुक्स लाइक। Oh no, it's not going to work that way. All right, I'm gonna try to copy. Don't worry about it. I'm just trying to copy that file here. Let me check first. It's just that there is another person in the lab and I don't want to disturb them, so I had to move to, this different lab. And the computer is actually there, so remotely doing on it. Anyways, I'll show you how that works. We're gonna copy that file from SSH here. So SCP means secure copy, and then copy from this location. Oops, Argon, and we have a data file there. So that is what we want to copy to our location. It says no matches found. Copy from to. Okay, let's write actual file name. Okay, so it copied the file and it should be in my computer at this location. Documents. Let's go there. That's a little Aperture. There it is. Argon 1 dot data. And let's open it with open 18 OVITO. And there it is. That is what it looks like.
Oh,
So you can see what lamps actually did. It created, that box and it filled
box.
argon
And,
atoms there.
and some
Uh,
items are out of the box.
they might look like because of the visualization. This is one thing actually.
Oh, okay,
So
okay. No.
it's a good thing you asked me, so I can actually tell you because I was also worried always, like, why is this atom outside of the box? And then slowly I realized we never really defined the radius of that atom, right? So that
Yeah,
radius
nobody.
is just a imaginary thing so that you can see atoms here, which we can actually control. Let me see, how do we exactly control that? Particles, radius, there it is. See that? I can actually control it to say 4. And there you go,
Okay.
right? If you look at actually X, Y, Z value of any of these atoms, they have to be within the simulation domain. They have to be within the simulation domain. So this is what LAMMPS essentially did for us when we ran uh, this much of
Mhm.
commands, this many commands. This is what
Mhm.
LAMMPS did. It sets up everything and then it creates a simulation box and it fills the atoms and that's it. Fills the atom
Mhm.
and then entire simulation box information is written to this data file which we are looking at in OVITO,
Okay.
right? But we want to go beyond that. We want to really do molecular dynamic simulation. We want the argon atoms to move.
Okay.
So let's go ahead and look at argon lamps file. So we want them to move, right? Um, for that, I can just go ahead and do this. Nano argon 1 dot LMP, and we can create velocity. We can give velocity to the atoms in that simulation cell. So up to this point,
It's clear, please.
this is what LAMMPS is looking at up to that point.
Mhm.
Okay, this is what LAMMPS is looking
Mhm.
at. Now we need to give these atoms some velocity. Okay,
Mhm.
and we can do that by writing velocity to all
Mhm.
the atoms,
Mhm.
create, this is probably the temperature in Kelvin, which is 1, very small,
Mhm.
I think.
Mhm.
Let's set that to 100. And then this is a random num. So in order to generate a random number, they need some seed value. And this is just a random number. You can put whatever random number you want, and
Mhm.
it will help lamps create a random number so that it pulls those Gaussian distribution wale numbers
Mhm.
so that your velocity is nicely distributed, of all the atoms. We can look at the uses of this command to use that more here. Here, velocity, and in the group ID. Group ID is the group of atoms to which you want to assign the velocities. कि कौन से atoms को तुम velocity देना चाहते हो. That's what the group ID is. हमारे केस में हमने well, हम है ना एटम्स का ग्रुप भी बना सकते हैं एक्चुअली. लाइक हियर मैं यहाँ पे लिख सकता हूँ कि ग्रुप ग्रुप type 1. That means all the atoms that are of type 1, group them, okay? And let's call it some group. I'll call it my group, okay? My group of atoms, okay? So I can, group all the atoms and call it something, like I can give it a name so that I can refer to that. And then after that, I can give velocity to only those atoms. Like here, my uh, group of atoms here. So you can see now I am giving velocity to only those atoms that I have grouped here, right? This is useful when you want to simulate, when you want to do different things to different atoms, different molecules, different set of things. Like for instance, जब आप आर्गन में या किसी सिस्टम में, नॉट नेसेसरली आर्गन, हीट ट्रांसफर स्टडी करना चाहते हैं, एक तरफ हॉट वॉल है, एक तरफ कोल्ड वॉल है, तब आपको ना एटम्स को ग्रुप करना पड़ेगा कि I'll group these atoms in and call them hot wall atoms, and I'll group these atoms and call them cold wall atoms, है ना? So that you can give these guys a different temperature and these guys different temperature. तो उस तरह का कंट्रोल अलाउ करता है, उसके लिए आपको ग्रुप करना पड़ेगा उन एटम्स को. Okay, so we know what group ID is, and then there is a style which can be, do you want to create velocity or do you want to set velocity or scale them, ramp them, or do you want to change them all to zero? What do you want to do? We wanted to create, so,
Great.
right? We set a style to create. And then after that style, argument we can provide. So for create, the argument is temperature. What temperature do you want to create? Okay, so you have to write TEMP, which is basically temperature value, and then the seed, which is random number generator random number. Okay, it has to be positive. That's what LAMMPS tells you. So that's what we are doing here. We're giving temperature 100 Kelvin. Oh, not Kelvin. I'm so sorry. Actually, the units is LJ. So whatever unit that thing is, basically 100 LJ units. That's the temperature basically. Okay, that's what we did. All right, perfect. So this is going to, give all the atoms velocity. So I'm now going to go and save this and exit and run LMP IAR1 LMP. Let's run that. Okay, we have hit our first error. LAMMPS says there is an error. This integer value in input script or data file is out of range. Oh, okay. That looks like it's probably a large number which shouldn't be there. So let me just go ahead and small it a little bit. Uh, okay, it successfully ran. There is some warning which we don't have to worry about it right now. We can look at it later. पर आप देख सकते हैं कि लैम्प्स ने रन कर दिया है इसे, right? So the only difference that was there is we grouped those atoms and we initialized their velocity, right? That's what we did. We still did not simulate the motion of atoms. Anyways, I want to show you कि वो जो डेटा फाइल है ना, argon1 डेटा फाइल, उसमें वेलोसिटी है कि नहीं ये देखो आप. ये देखो, वेलोसिटी इज हेडर एंड देन टाइप 1, सॉरी एटम जो पहला वाला है उसकी वेलोसिटी देखो आप. Now these atoms have velocity. See that? So that one command velocity create actually gave these atoms velocity. And we can see that here, right? If I open this file in OVITO, you won't be able to see because they're not really moving, but they have velocity property associated with them.
Okay.
So we have to get them to move so that we can see things. Okay, perfect. So pair style. Pair style.
Can we include everything now?
Say that again.
Can we include now everything and see the final version?
Yeah, of course, we can run that. Okay, you wanna see? Let's run it and see that. Also, so let me just give you a little bit of what it is doing actually. Pair style basically tells that, okay, this is the formula that I want to use to model the interaction between argon atoms. And this is cutoff value, which I'll show you what it means later. And the pair coefficient is basically the constants that are needed to solve that expression, that mathematical equation. We are creating velocities, and then this is the molecular dynamics simulation. Actually, this is the velocity Verlet integrator algorithm, along with Nose-Hoover thermostat, which will try keeping your temperature to this LJ units of temperature. And then this is another parameter that you can control about thermostats. And then Thermo 100 basically tells lamps to print the thermo information, temperature, pressure, density, energies, and everything else every 100 step. And then you are saying lamps ki, can you run it 1,000 time steps, right? So that's what you're basically doing. But you never really asked your lamps to write the data file, right? You're not really asking in this file. So you have to
Yeah.
include that as well, right? So let's do that so that we can actually save that information and see it.
Okay.
So here I'm gonna write, we can write dump. So dump is like, dump everything in this file. So that is how we write trajectory or how atoms are moving. That
Mhm.
information we can save in a text file. Let's look at the command of this first and how to use that. Here, dump, and then you have to give it some ID. So let's give it some ID, call it Argon's moving. So that's the ID that I'm gonna give it. And then group ID. So group ID is the atom group,
So
right?
here all, right?
Yes, we have created. Well, here we have not created, but we can just write all actually. All is the group ID that lamps create or creates automatically. lamps अपने आप ही सभी एटम्स को ना एक ग्रुप में डाल देता है, उसे कहते हैं
Okay.
all. तो आपको क्रिएट नहीं करना है, फिर वो lamps ही क्रिएट करके रखा है, तो we can just say all.
Mhm.
We have a style, which means atom. You can basically, in place of a style, you can write atom or any of these values. I'm just gonna say custom. Um, Let me see custom. Where is that? There it is, custom, which
Mhm.
means I want to describe what information should be saved in that dump file. That's what I'm telling labs कि custom
So,
मतलब मैं डिसाइड करना चाहता हूँ कि क्या क्या इन्फॉर्मेशन तुम्हें सेव करनी है उस डंप फाइल में.
mhm.
मुझे सिर्फ एक्स वाई जेड नहीं चाहिए, मुझे वेलोसिटी भी चाहिए उसमें, मुझे फोर्सेस भी चाहिए, एटम्स पे कितना है वो मुझे मुझे यू नो मुझे और भी कुछ चाहिए एटम के बारे में,
Mhm.
तो
Mhm.
वो चीज उसके लिए कस्टम मुझे लिखना पड़ेगा. एंड देन आई हैव टू डिस्क्राइब व्हाट डू आई रियली वांट,
Mhm.
right? So for custom, let's see what are the possible values. Possible attributes custom के लिए. You can output ID of that atom. You can output which molecule it belongs to. You can
Mhm.
output which processor calculated in its information.
Okay.
And you can also output their XYZ values.
Mhm.
And what is this? I'm not, well, I have to read again.
Mhm.
Unwrapped coordinates and so many more. All these things, of course, are described later, and we can read them. These are scaled coordinates. Okay, it doesn't matter. We just are going to save some small little information. And also let me look at the uses. Here is how we use that. Okay. So custom, and then there is every 100 time step. So let's just do that, every 100 time step. And then the name of the file I need to write. So I'm just gonna call it argon.trj, trj for trajectory. You can give any other letter to it. And then ID is the atom ID. Okay, 1, 2, 3, 4, 5. And then type of that atom. We don't really need to notice type of the atom. We know all of them are one. There is no point really saving that information. And then X and Y values. I'm just gonna write X value, Y value, as well as Z value. We can also write velocity in X direction, velocity in Y direction, velocity in Z dimension. We can also write what is the force acting on that atom in X dimension, what is the force acting on that atom in Y dimension and in Z dimension. We can save all that information and many more. Let's just save
Mhm.
these and see what that looks like. And then run lmp iar.lmp. And it's done. I mean, it's just 1,000 steps, so it's pretty fast. All right. And then you can see now we have ar.trj. I'm gonna show you what that looks like. First, I need to copy that to my computer.
TRJ means
Copied.
trajectory. Trajectory.
Yes, that's the convention that I have used. You don't have to do that way. You can save it, you can just call it AR. That's it. It doesn't matter. But it helps saving with that name. Let me give it data. There you go. So that's your Argon system, and you can see we have 10 frames. Why do we have 10 frames? Because our dump was every 100 time steps, and we have total of 1,000 time steps. So we have only 10 frames.
It looks real.
So if you play, this is what it looks like. Okay, it is in the loop, so it's not that fun actually. Even better, I can go add modifications and look at color modifications, color coding, and then I can operate on particles. Property, I can give it some, say I want to look at the force in X dimension, like Fx component of force
Mm,
on each atom. That's what I want to color it by.
mm,
So you can see here, um, this is, do you see this little XYZ, like a reference
yeah.
coordinate system thing? So this atom is experiencing a lot of force in X direction. That's what I can tell you by the color.
Mm,
And I can color those atoms by the force component because I saved that information in my trajectory file.
mm,
I can do the same with velocity. So like here, instead of force, I can color it by velocity in X direction. And you can see that has velocity higher in X dimension. And that is roughly 3.3 in value, I
mm.
guess. So yeah, this is a very simple one. Let's do a little longer and see what that looks like. I'm gonna have to modify the AR.LMP script a little bit then. But nothing fun is going to happen, to be honest. Not for now. There you go. 100,000 steps, sorry, 10,000. And it's done. Should we done it a little longer? Also, let me just go ahead and write this dump information a little slower. So I want to say more data every 10 steps. That will be a little. Oh, okay, so that ran for 10 seconds. And also when lamps finishes, it will tell you certain information which is of your use actually. This part. You can see how many time steps it can calculate per second, right? Yeah. And how much data you can generate per day. So that's like performance. That's the speed of your simulation calculations. Okay. It also breaks down that speed it also breaks down the time that was utilized in entire simulation into different parts. Like what was the time, how much time did pair calculation take? How much time did neighbor building take? How much time was involved in, the process of talking to each other? In this case, it will be probably, yeah, it's zero. It's because we are using only one core and it does not really need to communicate with another core. So, oh, all of them are roughly zero. Uh, and the modify command, we'll see more what those things are later. Let's go ahead and look at that now. Trajectory file. This is going to take some time to copy. And this file is way bigger. You can see that.
Mm.
Okay, we have the file now. There we go.
That's all we have 10,000 steps.
Yeah. So that's what they're they look like moving. Um, it's not going to be very much fun, but you get the idea how it's working, and we have still not looked at how we are really modeling the forces and what coefficients are going into solving that force model.
Can we see this tomorrow?
Yeah,
I think it's too much for me.
yeah. I'll share the resources with you.
Yeah.
This Argon wala simulation
Okay.
and also the other one, Python code, a little bit of whatever we did.
Hmm. Yeah, you can share tomorrow also, not a problem. Yeah.
It won't take too long actually. Tomorrow, I'll just do it right away. There is no point leaving it on tomorrow if I have right now time.
Hmm. Okay.
Yeah.
Yeah, so we can discuss more about how to, what values, what graphs we can generate from these simulations, and what are the more theoretical aspects of this function.
Yeah.
Yeah.
So while going forward, it will be really important that we learn what is a neighbor list, how often should that be built, um, what are, of course, force models, and many more things that come in molecular dynamics part. Because without them, even writing these things will be very hazy and it will just
Yeah,
be
yeah.
time wasted.
I understand.
So, so yeah, I'll also try including that.
So I can
The
get those theoretical information from that lamps what is that workbook, right? What
manual.
was that manual? Yeah.
So yeah, reading manual is great. That's how I read many commands that I needed and learned them. Um, but to study molecular dynamics, uh, there are other books, right,
Okay.
that we can use. There are many books, but I can share with you number of concepts. Like आपको पता होना चाहिए periodic boundary condition क्या है, आपको पता होना चाहिए neighbor list क्या होता है, आपको पता होना चाहिए एलजे क्या होता है फॉर श्योर, आपको पता होना चाहिए कि इलेक्ट्रोस्टैटिक फोर्सेस कैसे सॉल्व करते हैं, मतलब कौन सा थ्योरी है उसके लिए एटलीस्ट
हाँ
दैट
theory.
इज व्हाट। हाँ, और मिनिमम इमेज कन्वेंशन क्या होता है, बहुत इंपॉर्टेंट है अगर आप कभी डिफ्यूजिविटी कैलकुलेट करने वाले हैं तो। पीरियोडिक बाउंड्री कंडीशन एंड मिनिमम इमेज कन्वेंशन सुपर इंपॉर्टेंट। होल मॉलिक्यूल्स क्या होते हैं, ये सारी चीजें ध्यान में रखनी पड़ेंगी अगर कोई कैलकुलेशन करना है तो। फॉर इंस्टेंस अगर आप डिफ्यूजिविटी कैलकुलेट कर रहे हैं बिना मिनिमम इमेज कन्वेंशन के, तो आपका डिफ्यूजिविटी कंप्लीटली रॉन्ग होगा। तो लैम्प्स नहीं बताएगा आपको कि तुम इंक्लूड कर रहे हो नहीं कर रहे हो, वो बस डिस्टेंसेस कैलकुलेट करेगा और आपको देगा। आपको उस चीज का ध्यान रखना है कि क्या मैं उसे इंक्लूड कर रहा हूँ